Hello and welcome. In this video, I'll be talking about score matrices and how we can use them to quantify the goodness of an alignment between two sequences. So consider the following alignment, or consider two alignments between two sequences. There are multiple ways, of course, to align these sequences. Which alignment is a better one? So this depends on the number of matches between the two sequences. But is there a way that we can tell systematically which alignment is better? So there are a few approaches. So the simplest is simply sequence identity. So this would just be the ratio of identical positions to the total number of positions, or the length of the alignment, and times 100 if we want a percent. Another option is a percent similarity. So we might decide that some positions, though not identical, are somehow similar to each other. And we'll get more into that. And this is another metric, percent similarity. So some rules of thumb, if you're looking at alignments, if you have something like 40% sequence identity, usually this means you have some kind of homology. This is not going to happen by chance if you have greater than 40% sequence identity. For especially larger sequences, then this indicates that they're related. 20 to 40% is tends to be in the realm of ambiguity. So homology is likely, but might not be the case as well. And less than 20%, it's possible, but we're increasingly unlikely. These are just heuristics, and they're not absolute. So how about scoring a match between two sequences? If we have 100 amino acid proteins sequences, in fact, there are 10 to the 75 ways to align them if we allow gaps in those sequences. So this is a lot of possibilities, and we can use scores to measure the quality of these many different alignments. And we can calculate a numerical value for the overall similarity and rank these alignments. So some things to keep in mind. There is such thing as an optimal alignment. This would be the best scoring alignment. But there are also suboptimal alignments that might have slightly worse than the best score. And it's really important to keep in mind that the optimal alignment is not necessarily the correct one, the biologically correct one. So let's look at substitution matrices. And here we'll use a linguistic analogy, two words, the English word biology and the Swedish word biologi. And here we are looking at an identity substitution matrix. So this is the simplest case where basically if we were looking at a position in an aligned pair of sequences and they both have a B in them, then we would score this as a 1. And likewise for any of the other perfect matches. So a G with a G would be a 1, and any mismatch would get a 0. But following this linguistic analogy, we notice that the letter Y here and the letter I here, somehow these are similar. And we can imagine that if we were doing some kind of linguistic analysis, maybe we would want to penalize this mismatch, less than say a Y with a Z or Z. So in this way, similarity somehow is important. So you can imagine a more nuanced score system where if you had a perfect match, of course, you still get a 1. And then if you have a really bad match, for example, for mismatched consonants, so a G substituted for a B is not a good sign. So that would get a -1. But then maybe vowels, we would not reward the same amount as a perfect match, But if we saw an O substituted for an I or a Y substituted for an I, maybe vowels we would give these 0 points, so not penalizing them quite as harshly. And then with one of these score matrices or substitution matrices, you would then score an alignment. So imagine this particular alignment where we've introduced 2 gaps here, and we're proposing that the B here is paired with the O, the I here with the L. And you would go in and just sum up these scores. So B paired with O, we would look this up in the matrix. So B with O is a -1. Of course, it's a mismatch. And you would do this for all of the subsequent pairs. And we would be left with a -2 as our final score at the end. And then, of course, with this alignment here, which is clearly the best one, we would get perfect matches, so ones here, but then in the last one, the substitution Y with the I, we would reward that with just a 0 instead of a 1. So the maximum possible score would be 7 out of 7 characters. But this would turn out to be probably the best alignment, the best score we could possibly get with these 2 sequences. So there are different types of scoring systems, right? There's identity, positive scores for identical residues, and this is what's used for nucleotides because there are not so many options. There's only 4 of them. And so really simple scoring systems tend to be used for nucleotides. But for protein amino acids, we tend to use similarity more. And this is because different residues have different relationships, and some residues are somehow more different than others. And there are different ways to quantify this. So it could be based on chemical differences or perhaps an evolutionary perspective, how often they're mutating. And so there are different ways of deriving score matrices for amino acids, and they come from different things. Some of them are based on theoretical mutation, models of mutation, physical chemical properties, and some of them are based on empirical measurement. So if you remember amino acids, they have different physical properties. So some of them are charged, some of them are positively charged, some of them are negatively charged, some of them are hydrophobic, and some of them are hydrophilic, water-loving molecules. And this determines, of course, how proteins fold, but this also gives us information about which substitutions maybe might be more likely. For example, we might be more likely to see a positively charged amino acid substituted for another positively charged one than to see it substituted for a negatively charged one, which would have a big effect on the structure, on the structure and therefore the function of the protein, and more likely be penalized by evolution and natural selection as a result. So we have these scoring systems, and most of them work the same way. You have an observed or kind of a model frequency of the substitution, and it's being compared with your expected substitution. So the probability of just based on the rate of occurrence of these amino acids. So how likely is it, if we're assuming just completely uniform random substitutions, no physical influences or anything like that, and we know, say, the frequency of one of these residues is extremely low, then we would, for example, expect it to be less likely that an amino acid turns into this really rare amino acid. So this is just based on their observed frequencies in general. But then you have non-random models. And these are the ones that take into account the correlation between these residues, the physical correlation or the evolutionary correlation. And then often in these score matrices, the score values themselves are represented with something called the log odds ratio. And basically these logs are just easier to deal with. So often when you're dealing with probabilities, you're multiplying numbers. Like if you, the probability of two things co-occurring is a multiplication. But when you take the log of things, then multiplication becomes addition. So it's a simple way of creating an additive score with a multiplicative quantity. So there's some particularly prevalent examples of substitution scoring matrices, and one of them is called the Pam matrix, and this was introduced by Margaret Dayhoff in 1978, one of the founders of bioinformatics. And Pam is short for percent accepted mutations or point accepted mutations. And this is accepted in the evolutionary sense. So this is a mutation that was accepted by natural selection. So that is kind of the thing to remember about this model, that it's based on a model of evolution. So the data that is used to generate these scores comes from observed amino acid substitution frequencies in closely related families of proteins. So like you would take sequences from the globin family or from the insulin family, for example. And then multiple alignments are done on sequences that come from that family. And so we have this unit, 1 PAM, one accepted amino acid change per 100 residues. And this becomes a kind of metric of evolutionary distance. So like PAM 250 then would be PAM raised to the 250th power. And then this is like saying this is a greater evolutionary distance, right? Because you have more substitutions per 100 residues. So when using these matrices, it's appropriate to compare sequences of similar evolutionary distance to the matrix you're using. So a PAM 120 should be used for sequences that are approximately 120 PAMs distant from each other. So here's just a bit more what we mean by this. So like if we had a stretch of amino acid, 1 PAM would be, one of these, a single substitution on average. And we mentioned this log odds. So score in a PAM 120 matrix reflects the log odds ratio or the ratio of a particular substitution probability relative to its chance of occurring randomly, just based on how common the amino acids are. The log odds ratio of substitution pair for two sequences that are 120 PAM units apart. And so, yeah, so how do you use this matrix? It's the same as the biology example we showed. So you would have, say, two sequences that are aligned with each other, and then a pair of amino acids, and you would just look up that pair. So for S and T, we would go here to S and find T and the corresponding score associated with that, and you would just sum them up. So a higher score is better. Another score matrix that's out there is the another score matrix that's out there is the Blossom 62 matrix, or the Blossom family of scoring matrices. And this works a bit differently from PAM. So in this case, there's no model of evolution that's being used. And instead, the sequences that are used, the data that's used to generate this matrix, they come from less closely related families. So sequences that are much less similar to each other than PAM. And then what's done is they're clustered. Sequences are are first clustered according to percent identity. So you would pick a threshold, say 62% identity of these sequences, and you would take a group of all of those sequences that satisfy that threshold of 62% identity and perform multiple sequence alignments on them like this. So you would try to align them, look at the conserved regions, and uh, and so if we have say blossom 50 or blossom 40, changing the percent identity, the threshold that we use to accept sequences in there, this becomes the way of creating greater distance or greater difference between the sequences. So instead of evolutionary distance, we have this threshold, but it's kind of similar in the sense that if you have a lower threshold, then you're going to have more sequences that are different from each other. And the higher threshold, the higher percent identity, you're going to have fewer sequences that meet that requirement. And just kind of going through how these numbers are generated, like let's say you had one of these multiple sequence alignments here. So in each of these columns corresponds to like a position, like one of these columns here in this multiple sequence alignment. And these rows here then are individual sequences that have been aligned with each other. And you have different amino acids occurring in each column. And to generate the score, you go through a series of steps. So the first step would be to count just the total frequencies of occurrence of each of these amino acids. The second step then would be to count the frequencies of occurrence of each possible pair. So for instance, HI here is a pair. And going in one column, we would have, say, one pair of HH here, another pair of HH here, another pair of HH here, also this pair of HH here, like all the different combinations of different pairs. And you would sum those up and divide by the total. So for each type of pair, then you would get a frequency. And then so then this becomes like your this becomes your observed frequencies, and then you have an expected frequency of occurring. So these then are just the base frequencies multiplied with each other. So if we wanted to take if we want to get the expected frequency of the HH pair occurring, it would simply be the probability or the frequency of H occurring times itself. So it's the probability of both things happening at the same time. And you multiply these by 2, and this is because you're testing for both the substitution of H for H in one direction and also H for H in the other direction, or likewise the substitution of H for I as well as the substitution of I for H. So you multiply these expected frequencies by 2. So then you have these 2 different frequencies. You have the observed and then you have the expected. And then this is how you generate your score. So you calculate this log odds ratio of the observed versus the expected, and then take the log of this, and then this gives you the scores for the blossom matrix. So here are just some examples. So running the Pam matrix, yeah, it's a bit small to read here, but we can take 2 sequences and match them up with each other. So here's an example. These are from antibodies, and we have one from mouse, one from human, with rough correspondence between them. So you can see here the V and the F are aligned here. And then just going through each pair and checking in the Pam matrix what score results from it, and then producing from this a sum score of 815 in the case of this human compared with the mouse, And then you can see there's a better score for human compared to this macaque, the monkey, these two proteins. Likewise, you can do the same thing for the blossom matrix. It works the exact same way. You just go through each position and check the pair. Here we've got identical matches, identical matches. You know, at some point we run into a mismatch. Here's K for Q. So you would look up the substitution score for K and Q in the matrix. So summing up, Pam models, these are evolutionary distance. They're based on closely related members of a family and a phylogenetic tree. Blossom matrices, they're not, sequences are not longitudinally related. They're more based on sequence similarity, and it tends to be larger distances, more distantly related sequences. So some basic rules of thumb, some heuristics. Your choice of which matrix to use kind of depends on your situation. And if they're really distantly related, you would want to use larger Pam numbers, larger evolutionary distance, or lower blossom numbers corresponding with lower percent identity threshold to let in sequences. If they're closely related, then you want to use a lower number like Pam 120 or a higher blossom number like blossom 80. Likewise, for short sequences, you want to be careful. So like short sequences are less likely to change that much. So they should have very few accepted mutations per 100 amino acids. So a low Pam number is good, and a very high percent identity threshold for the blossom matrix. A lot of times though, for many applications, blossom 62 just gets used as kind of standard for ungapped matching. Blossom 50 for gapped matching if you have gaps in there. Scoring schemes for nucleotides. So these tend to be much simpler. So here's an example of a score matrix for nucleotides. And here you can see it's very uniform. So a harsh penalty -4 for any mismatch, and a reward 5 for matches. And you can have different scoring matrices. So some, depending on your application, you can have score matrices that are maybe different according to the GC content. So yes, and then now dealing with gaps. So we mentioned gaps, and these are things like insertions or deletions. So for example, we have 2 gaps here on the end, and then here we have some gaps in between. So these are examples of gaps. And yeah, so homologous sequences, they have different lengths, and this is due to things like insertions and deletions. So to align 2 homologous sequences, you will need to introduce gaps, because if you don't, then you'll have these frame shifts that will get heavily penalized because you'll have a lot of mismatches, when actually maybe inserting 1 gap would allow your sequences to align well again. So there's different ways to deal with gaps, and you can have gap penalties. And you should have gap penalties, and this is because you can kind of abuse them as well, right? So you can have, you could have a small sequence, for instance, and just introduce tons and tons of gaps to force it to align with a larger sequence. So there are gap penalties. The simplest one is a gap opening penalty. So you introduce a gap, and you reduce the total score every time you do that. But then there's also a gap extension penalty. So maybe you want to grow the gap, and if sometimes you'll have a deletion that stretches multiple gaps, and it maybe doesn't make sense to penalize the extension of a gap in as much as opening the gap. So you can have different numbers for these 2 different things, and the magnitude depends on the setting. So it really depends on your a priori information. So if you have closely related sequences, then you're going to use harsher penalties. If they're distantly related sequences, you suspect they're homologous, but you're really kind of just looking for some conserved domains, this kind of thing, then you're going to expect a lot of gaps, and then you want to have lower penalties. So these are just some examples. So alignment B here has a higher similarity, but it's not necessarily correct. And you can take a look at some of the types of substitutions, gaps that have been introduced here. And yeah, just going more into detail. So yeah, there's the basic case. To introduce a gap, we can have a score minus D, negative D, that gets introduced, and just extending it linearly. So this is the kind of the dumb case, the easy, the simplest case. So if we add more gaps, then we just add more minus D penalties. But then there's this extension gap that I mentioned. So we introduce an opening penalty at first, but then for every subsequent gap that we add to that, we only reduce it by E, which would be maybe a smaller penalty relative to D. So that's it for this video. I'll talk about alignment of sequences, the algorithms we use to get those alignments in the first place. That'll be in the next video, so I'll see you there.